Hello and welcome. This is a Starling engine problem involving helium. So obviously we have to use the PG model because helium is a perfect gas by definition. Also the minimum temperature and maximum temperatures are supplied, and the Starling cycle is shown here in this TS diagram 1, 2, 3, 4. 4. Obviously the efficiency we already know is going to be same as Carnot efficiency. But important thing is to know that state 1 has the lowest temperature and pressure which are supplied in this problem, and state 3 has the highest temperature and pressure, which becomes obvious if you look at the cycle on this animation. The PV diagram is shown here. As you can see, state 1 has the lowest temperature and lowest pressure, and state 3 has the highest pressure. Of course, from the TS diagram, you can conclude they correspond to lowest and highest temperature also. So let me go. I'm pretty sure you might be familiar with the Starling cycle to be able to solve a problem involving one. So we'll go and let me just lead you through a solution here. First of all, to start the app, again, we'll follow the closed system specific route, and all the reciprocating cycles including Starling cycle, Otto cycle, diesel cycles this is the launch pad. And the model that we use is the PG model, obviously. And I've already solved the problem on this tab. So I'll just walk you through here. So first of all, the minimum temperature and pressure are recorded here so that we can use variables. They are all in SI units converted to Kelvin. And I'll talk about the remaining equations later on because they involve finding the thermal efficiency of the cycle. So let's go and see how the states are calculated. State 1, which has the lowest pressure and temperature, is simple. P mean and T mean is shown here. And as the mass is given to us, and of course helium is the fluid which has been selected. For state 2, again, for state 2, we do not know, if you notice, the specific volume, which must be equal to state 3. So actually, when we try to calculate state 2, the V3 has a white background because state 3 is not yet calculated. The temperature doesn't change. It's a constant pressure heat rejection process. So temperature is known, and the specific volume is same as state 3. Mass doesn't change. But this is calculated once we know how to find state 3, because for state 3 we know maximum pressure equals the pressure and the maximum temperature equals the temperature, and mass is known. So state 3 is completely evaluated. And now we can go back to state 2 and calculate it, or click the super calculate button. Either will work. For state 4, again, state 4 is it's a volume, constant volume between state 1 and state 4. If you go to the animation, you can check that. And the temperature remains constant because heat is added between state 3 and 4 at constant temperature. As you can see here, 3 to 4, temperature remains constant. And if you go to the constant and the PV diagram, you can see, where is it? The PV diagram will show you that between 3 and 4, temperature remains constant, but 4 and 1, the volume remains constant. So that's how we get to know state 4. Everything is known, mass is constant. In the graphics panel, you can just see that exactly the TS diagram as we anticipated, 1, 2, 3, 4. You can also do PV diagram. It should be kind of similar, 1, 2, 3, 4, as we saw in the animation. In the process panel, it's quite simple. We load state 1 and 2 for process 1 and just calculate to find all the unknowns. 2 to 3, again, we know that 2 to 3 is a volume constant, so automatically the boundary work is calculated to be 0, but we could also enter it if we wanted. It's kind of obvious. So if you just calculate, you will find that boundary work will be calculated by itself. State process 3 takes helium from state 3 to 4. Again, a calculate produces all the unknowns, and state 4, process 4 finally completes the process. Again, other kind of work is always 0. So WO is set to 0 in all these processes, and the rest of them are calculated by analyzing the energy equation. In the cycle panel, you'll notice that the thermal efficiency that is shown is not same as the Carnot efficiency. And what is the reason for that? Because in the cycle panel, all these processes are just put together algebraically without realizing that heat rejection from, if you go back here, heat rejection from state, see here 2 to 3 is heat is added, and here heat is rejected, but actually this heat goes from here to there. This is the regeneration part, and that's not captured in the cycle panel. So we recognize, cycle panel thinks that this amount of heat is also added in addition to Q in here. So really, heat added is only from 3 to 4. That's the external heat addition. Of course, the network is the net area. Network is calculated correctly. There is nothing to do with regeneration. So if you go back, you will see that the network is calculated correctly, and so this is correct amount, but Q dot in is not correct amount. This is not correct amount. It is increased because of the regeneration is considered a heat added here, external heat addition. So we correct that situation in the IO panel by saying, external heat addition is really, when you analyze process 3, the heat added was what went in. So if you go to the process panel and look at process 3, that's where the external heat addition happened. So this is our Q in the cycle. So therefore, now the efficiency is simply, thermal efficiency is given here, W net by Q in. W net is calculated in the cycle panel. So W net 1 is the variable name. If you go to cycle panel, this is a unique variable, W net 1. So that's divided by Q3 is our thermal efficiency. And that's when you click the calculate button, the thermal efficiency is found here, 72.3%, which is exactly the Carnot efficiency, as you recall. Of course, everything about the cycle is now known. Every other variable you want to find can be found either in the cycle panel or in one of the process panels. But always remember here that Q in and Q in any regenerative cycle, the Q in and Q out calculated in the cycle panel may not be correct, because they both will be increased because regeneration is added here and there, which actually are not external heat transfer.